Today we'll be looking at how to manage and analyze repeated measures data in SPSS. So here I have a simulated data set. These are not actual data. These are data that I simulated using R. And what we see here in these right two columns is memory score pre and memory score post. So we can imagine that this is a memory test that people took on a scale from 0 to 100, and that they completed this measure before and after something. And that something is a treatment. So people were either assigned to the treatment group, which is coded as 0, assigned to the control group coded as 0, or the treatment group coded as 1. People also were measured for whether they experienced a side effect, with no side effect being 0, and a side effect experience being 1. So treatment and side effect are both binary variables coded as 0 or 1 for absent or present. And lastly, we measured people's age and education. Education being number of years of education, with 12 years being completed high school, 16 completed a bachelor's degree. So, we measured people's memory before and after treatment, and we measured some other facts about them as well. There's a few ways we can analyze these repeated measures data. So repeated measures being because we measured memory score at different times. And there's also ways we need to transform our data to fit the structure that SPSS wants the data in for the specific analyses we might run. We'll come back to that later. For now, we can start by trying to analyze these data using a general linear model. And so the way we do that is we go to Analyze, General Linear Model, and again, this is repeated measures data, so we'll choose that option. We're then met with this menu, where it wants us to specify within subject factor. So within subject factors are things that vary over time that vary within a participant. And I sort of gave it away there. The thing that varies within participants here is going to be time. So participants completed, a measure at time 1 and time 2, so they experienced both of those levels. Whereas something like treatment, participants were either in the treatment group or not in the treatment group, and they didn't go back and forth between those groups throughout the study. Similarly, they didn't change their education throughout the study, presuming this was some sort of, short period that people experienced the treatment for. So we're going to create a name for this within subject factor, which we'll call time. And we're also going to specify the number of levels, and since we just measured pre and post, there's just 2 levels. So we can specify those things, then click Add. Having created our within subject factor, we also want to specify our measure name. This is going to be our dependent variable. That's going to come from memory score pre and memory score post, but when we just create one measure out of them, we'll just call it memory score. We can add that, and now we can click Define. So here you're going to see these 2 levels for this variable memory score, and so we can very easily see that this might be good places to add these memory score pre and memory score post variables. And now we'll want to specify the within subject factor as well, the between subjects factor, which is treatment, as we mentioned before. So we have a within subject factor of time. We put in the 2 dependent variables that measure it at each level of time, and we also specify our between subject factor, which is really the variable we're interested in this instance. We can also add covariates. Covariates are variables that we think might plausibly affect the outcome, but aren't necessarily variables of interest. So we don't really care in this instance about how age and education might affect our memory scores. We're really interested in the effect of treatment, but we also want to control for any variation they might cause in memory score. So we'll add them in the covariates box. Now we're going to go to Model up here at the top right. SPSS has many default options for all these analyses we might run, and here it defaults to this full factorial model. We're going to hit Custom just for now though. What we're seeing here is the variables we entered into the model, treatment, age, and education. We have build terms, which is going to be the way we can add these terms into the model. We can add them as interactions, main effects, 2-way, 3-way, 4-way, 5-way. We'll talk more about that in a bit. And between subjects model, which is as we add these terms over into our model, it will show us here so that we can get an idea of what the whole model looks like. So the first thing we're going to want to do is we're going to want to add main effects of all these variables. So we can select all of them and move them over here as main effects. Main effects is just the overall effect of the variable, and this is as opposed to interactions, which specify how the effect of the variable might change as another variable changes. So we might think that the treatment only works for people who are older. So perhaps people who are young don't need any treatment, they don't benefit from treatment on their memory, and so we wouldn't expect that treatment has an effect for people who are young. But perhaps for people who are old, who are dealing with memory issues, treatment might then be helpful. And so we might think that there's an interaction between age and treatment. And so we'll add this, we'll select both of them together, use this interaction term here, and add that there. And so you now see SPSS does age asterisk treatment, which is sort of saying age times treatment, which is the format we generally use to specify interactions. And perhaps we think there's also some sort of interaction between treatment and education. Perhaps for people of low education, this might benefit them more, and so we'll add that in there as well. And so now we can click continue, given that our model is now fully built. There's other options we can select here as well, for example, contrasts. Contrasts are more useful when we don't have binary variables, but instead have multiple, more than two levels of these independent variables. Because if we find a significant effect of, say, time, but there were 3 points at which we measured participants, we don't know if it's a difference between time 1 and time 2 and time 3, time 1 and time 3, and so that's where contrasts become useful. But given that we only have 2 levels of, the time and treatment variables, we're not really going to use that here. We also have plots, so we can create graphs of our results, which is very useful. And so here we'll specify that time will go on the horizontal axis, and we'll have separate lines for treatment. So we should then see, 2 different lines for treatment, and if we are correct that treatment has some sort of effect, we should see that the slope for the 2 treatment groups differ. So for one group, they have a certain level of change over time, but for the other group, maybe the treatment group, their memory scores, improve more over time, and so that slope might be a little steeper, but we'll see in our results in a bit. And so once we've selected those 2 things, we can select add. Now we can specify the type of chart. Usually with categorical variables, we choose bar charts rather than continuous variables using line charts. We should always include error bars to visualize variation in our outcomes, and we'll leave those as confidence intervals, and we can click continue. Another very useful thing is estimated marginal means. So oftentimes in these analyses, we get some sort of test of our term of interest like treatment, but we get things like f-tests, sum of squares, which aren't really that interpretable on their own. And so what we really want to be able to do is to interpret our results in the form that they were collected in. So if we want to see differences in memory scores, we want that, in the measure of, the memory score on the 0 to 100 scale. We want to say, what was the average, treatment score, pre and post? What was the average, memory score pre and post for the treatment group and for the non-treatment group? And so we can do that with estimated marginal means. So overall, it's just going to be across all participants, across groups, what does the model estimate the mean score was in memory, and also, by treatment group. And so we'll do both of those. And so we can also select compare main effects. We won't worry about this for now. So we're all set here. Rather than clicking OK, I'm going to click paste, and it's going to create a new syntax file, and I'll talk about that in just a minute. So here is our syntax file. I just opened one up, but it will automatically create one when you click this paste button. And so we are now on the syntax file again, and we can see it starts with this dataset activate dataset 1. That just happens because SPSS will sort of add that in, because if you have multiple datasets, you need to specify to SPSS which one you're working on. So always make sure that if you do have multiple datasets open, that you're working with the right one. In this case, we just have the one open, so that opens as dataset 1. So what the syntax is essentially what's going on under the hood when you're, running commands from the point and click menu of SPSS and just clicking OK when you finish that analysis. So we see that here are the variables we entered into the model. Here are the, between subjects factors we entered, and here are the covariates we entered. So we specified a within subject factor, time, it had 2 levels. We specified our dependent measure. This is sum of squared types 3. It's a way, it's an important part of the model, but we're not going to talk about that right now. We created a plot. We specified estimated marginal means, and our alpha level is 0.05, which is the standard alpha level used, which specifies that we will only consider our hypothesis supported, or consider, there to be sufficient evidence of an effect existing if there's a less than 5% probability that we would observe results this extreme, assuming if there was no relationship between the two variables in the data, or in the population rather. And so lastly, we have our design, which is, if we specified all our variables, we still don't know how they work together. So we did specify interaction terms, and so you'll see those there with the age times treatment, education times treatment. And so what we can do now is we can select all this, and we can hit this green button up top to run the model. This will then generate an output file, which produces all of our results. So there's much we'll see here. First, we'll just get a breakdown of how many people were in the treatment group versus the control group. We see roughly even, 251 in the control, 249 in the treatment. Here are our multivariate tests. We're not going to talk too much about this right now, but essentially what it's doing is it's saying, for all the things we specified in our model, treatment, age, education, treatment by age, treatment by education, how do those interact with time, and also what's time's overall effect. So what we're seeing here, this last column, sig, stands for significance. This is the p-value, or the probability of observing a result as extreme as we're seeing if there were no relationship between the two variables, or the term, if in the case of these interactions, and the outcome variable, if there was no relationship in the population. This is a very contentious issue within statistics. I think it's widely recognized that this is not the best and purest way of analyzing data, or making conclusions from our data. But the reason we use it is essentially saying, if there was no relationship in the data, we probably wouldn't expect, no relationship between the variables in the population, we probably wouldn't expect to observe extreme results. So when we start seeing results that are very extreme, if those are very low probability results in a situation where there's no relationship between the variables and the actual population, then we might conclude that, there's probably something going on here, and that there probably is some sort of relationship. So what we're seeing here is these, very small numbers, less than 0.0001, 0.001. Again, we use that alpha threshold of 0.05. So this is less than 0.05. So we would, it looks like here we have a significant effect of time. Likewise for the interaction between time and treatment, which is sort of the key term of interest. So we want to know, does being in the treatment group change your effects, your scores on memory pre versus post? Likewise, there's a time by age interaction. So how you do on the test pre versus post depends on your age. And again, a time by treatment by age interaction. That's a 3-way interaction, which those can be tricky to interpret, so we'll just leave that be for now. There's also the test of severity. We're not going to discuss that for now. The test of within subject effects might be a little more what we're looking at. In this case, it yields very similar results as our multivariate tests. The reason for that is that we only have 2 levels of our within subjects variable. So in cases where we do have, maybe 3 measures, at 3 time points, we might see different results here. And in that case, the tests of veracity become important, which is, again, only relevant if you have 3 or more levels. But in this case, we don't have it, so it's not something we're going to cover here today. But again, results are kind of the same here. We see these significant effects for time, time by treatment, time by age, and time by treatment by age. Here in the tests of within subject contrast, showing something very similar, significant effects across all those variables. Here's where we get that type 3 sum of squares. And again, those numbers don't mean much to us, neither do the f-tests. So we really want to be able to get these variables or these, effect tests in the raw form using estimated marginal means. And so if we come down here, that's exactly what we get. So the model estimates that, kind of averaging over other variables, which we can see here in this footnote. There's averaging at the covariates, with age equal to 37.5, education equals 13.2, and this is also sort of averaging across treatment group. We're seeing an estimated memory score of 73.5. It's averaged across time as well. And so now we're also getting this estimated marginal mean for treatment, which is, a mean of 71 in the treatment group, a mean of 76 in the control group, a mean of 71 in the treatment group, a mean of 76, which is suggesting that the treatment group had higher memory scores. But again, this isn't exactly what we want. What we're interested in is, does the treatment group scores, between the two time points differ from the control scores between the two time points? So essentially, we want to know, sometimes it's called a difference in difference. So the difference being pre and post, and the difference in the difference being control group versus treatment group. And so we're not getting that yet. And so what we can do is we can go back to the menu to change some things about our analysis to get different statistics here. And so rather than running this through a GLM again, what we're going to do is we're now going to transform the data, and it's going to be easier to get these results that we want in this transformed form. So what we have right now in our data set is we currently have the data in what's called wide format, which means that our dependent variable exists in multiple columns. And for each participant, there's just one row. For this next analysis we run, we're going to want the data in long format, which is we're going to have one column for the dependent variable, and then a row for every participant for every time point at which data was collected. So here there'll be one row for memory score, and then a column for participant 1, time point 1, a column for participant 1, time point 2. The way we do this in SPSS is we can go to Data, Restructure. And what we're going to do is this first option here, which is restructure selected variables into cases. So you can see the data here kind of going from wide to long format, and that's the one we want. So we'll hit next. We're just going to be converting one variable here, but if there were multiple variables, imagine you had memory score pre-post, and then attention score pre-post, and so on, you might want to convert multiple at a time, but we're just doing the one for now, so we'll leave that. Now here, it's going to specify, what variables we want to kind of move around. So it's going to create an ID number. So obviously when we, now have multiple rows per participant, we want to make sure we know what participant is in what row, and is this, a participant's second row for their data, or is this the next participant's first row, etc. So it'll just automatically create a variable called ID, which we can leave. That's just fine. Now, we're going to have some fixed variables. So fixed variables are the variables that are not going to change at all. So we don't need to transform age, education, treatment, or side effect. Those variables are all going to stay the same, so we'll add them to fixed variable. Now we have this target variable, which is the variable to be transposed. This is the main reason we're doing this. And so our variable of interest here is memory score. We want to get one column for memory score. So it's going to have target variable, which is the variable it's going to be transformed into, so we can name this something better than trans1 and call it memory score. And we're going to add in these variables of memory score pre and memory score post. And so now these two variables are going to become memory score after we, complete these next steps. So how many index variables do you want to create? The index variable is what's going to store the, whether this is a pre or a post measure. So we obviously want to know that. Kind of by default, it's going to, transform them in a structured way, but we would just want to be able to keep track of that just for our own sake. So what ends up happening is that, this first variable here, memory score pre, is going to go into the first row, memory score post is going to be the second row, so whatever order they are, in your data set, or at least whatever order they are as you added them here, I believe is actually how it works, is going to be the order they kind of come out in the rows. But we would just want to have an index as well to make sure we understand what actually happened. And so we just need to create one variable. It's going to take on a value of, pre or post. So we'll go ahead with that. We can use sequential numbers. So this could be, you just label them 1 or 2, but I'd rather have the labels of, pre or post. And so we can just do that here, and we can leave that as so. We can also rename it from index 1, and we can call this, time. We could change the index values as well, perhaps, or maybe not here on this menu. So we'll leave that as is. So we can hit next here. Now, this is an important step. It's going to say, what do you want to do with all the variables you didn't select? So if we go back to this menu here, we selected all these fixed variables, but what happens if we didn't, add those in there and we just left them over here instead? Well, at this menu, you get to say whether you want to drop them or keep them. I always just recommend keeping them. There's no harm. It's always better to keep them and delete them later. But really, when you're generally managing data, unless it's becoming very problematic where you're scrolling through your data to find things and there's just so many variables that it becomes very difficult, I recommend just not deleting data. It's the safest way to proceed. So we'll keep all the variables. For any variables that are blank, do you want to create a case in the new file or discard the data? We don't have any missing data here, so it doesn't matter anyway. We'll just keep the defaults, and we don't need to do anything about this right now. So now, in many of these windows in SPSS, we have these OK buttons, which runs the analysis immediately, or the paste button. We don't have that in this, restructure data wizard, but it has this menu instead, where at the end it says, click this button to restructure now, or click this button to paste the syntax. We always want to paste the syntax so that we can save our steps. So we'll use the paste and click finish. We'll go back to our syntax file, and now we'll see this VARSTOCASES function. So it has to create an ID variable, which was called ID. It's going to make a new variable called memory score from memory score pre and memory score post. We're going to create an index variable to know which one of those corresponds to which. We called that memory score. The index is over time, and it's for the variable memory score. And then we're keeping, all these other variables. And if we didn't specify any variables, if we missed any, we're going to keep those as well. So again, this is what our data looks like right now, where we have these 2 columns, memory score pre and memory score post. We're now going to run this function, VARSTOCASE function here. Here's just, some output that we don't really need to look at right now. But if we go back to our data, now we see there's 1 column for memory score. It specifies whether it's pre or post in this time column. And we have an ID variable, so participant 1, participant 1, participant 2, etc. So now our data are in long format. And for this next analysis we run, that's going to be exactly what we need. So we're going to run now what's called a linear mixed effects model. Sometimes this is also it's sort of a statistical implementation of what's broadly called multi-level modeling conceptually. And so the reason we do this is when we have sort of nested data. So here we have responses for memory score nested within participants. So participants complete multiple memory scores. The very classic example for when multi-level or linear mixed effects models is used is when you're, say, gathering data on students, multiple times per year. So the measures are nested within students. The students are nested within classrooms. The classrooms are nested within schools, within school districts, within states, within countries. So oftentimes in education research, they deal with these structured, nested data sets. And so there might be, variation that's, being brought to the data just by the participant that we can't really account for any measured variables. And so we would expect that, multiple measures from person A are going to be correlated with each other more than the other measures from participant B in ways that we can't necessarily adjust for in any, variables that we've collected. And so, that violates assumptions of independence, for typical general linear models. And so we use mixed models to account for that dependence instead. And so if we go to Analyze, Mixed Models, Linear, we get met with this menu. So first it's going to ask for subjects. So that's going to be that ID variable. So this is sort of the nesting structure that's being used. We have multiple measures for each participant, so we need to account for that, and so we do that with the subjects variable. We don't need to worry about any of these others here for this analysis, so we'll just click continue. And now it's going to ask us for our dependent variable, which is going to be memory score, factors, which is going to be treatment and time, and we also want, our covariates of age and education. There's multiple options, multiple menus here to specify different things. We'll just click through each one quickly. So again, we have this, build terms aspect. So again, we want all the main effects, so we're going to do all those. We're going to add those in. Most crucially, we want the interaction of treatment and time. That is, the key test we want to see. Does the treatment change how you change over time? So that sort of change and change, or difference and difference, is sort of, what interactions get at. And that's what we're interested in here. So we're going to add that. We also want, interactions between treatment and age, between treatment and education, and we also want those three-way interactions as well. So we want, does this, treatment effect, again, how treatment changes how you change over time, does that depend on age and education? So we'll add those as well. And so that looks like everything I want here. We have the main effects of our 4 variables. We have, how the treatment effect changes with time, with age, with education, and with those three-way interactions as well. And we might add one more here, actually, which is that, how you change over time might depend on your age. So from age 25 to 35, your memory might not change much, but from age 85 to 95, it might change a lot. And so we'd want to account for that as well. So we'll add that in too. Now we can click continue. Here's the random component. We don't need to do much on this menu because for 2 reasons. One, we only have 1 or 2 levels, where we have responses within participant. So we don't have to do any sort of complicated nesting structures where sometimes, the nesting is clean, which is like participants are within 1 classroom. But you might also have some sort of situation in your data where, the participants are within multiple higher level groups, 1 or more higher level groups, which gets more complicated. We also are not going to specify random slopes. So what we're doing right now is specifying random intercepts, which is going to say that participants are going to differ in their memory scores just sort of, at baseline kind of by default. And so we want to account for that. What random slopes accounts for is that, the treatment effect might differ by participant. So there might just be things that we can't measure about, why the treatment effect for you works differently than it does for me. But we're not going to get into that right now. It's also very unlikely that we'd be able to model that well with just 2, time points, because it becomes difficult to separate the, variance in the between person, variation in treatment effect from the treatment effect itself, given that there's only 2 time points. So we're just going to leave this menu as is. Estimation method, we won't get too into this right now, so we'll just leave this as is. Statistics, we can also generate some descriptive statistics. We want the parameter estimates for the fixed effects, that's important. And the rest of these we'll just leave as is for now. Now here's the estimated marginal means. Again, this is the part where we're able to get the results sort of in the raw measure that we care about in an interpretable way. So it's difficult to interpret f-tests and, sum of squares, but the raw score is going to kind of be able to tell us something. And so I'm just going to add all these in here, so we're going to be able to see what the model estimates just the sort of average score is, the average score in each treatment group, the average score in each, time point, and the average score in the interaction of treatment and time. So we want to compare main effects, and we'll leave the rest as is for now. So with all that, we have specified everything we need. We can hit the paste button. We'll go back to our syntax window. So now we see this mixed function here. We see the dependent variable, the factors we specified, and the covariates as well. Here we see a bunch of things. This is the way you calculate degrees of freedom. There's, it's a little more tricky in mixed models, so we specify that. The confidence intervals that we create are going to be 95% confidence intervals. This is things about, how many iterations is the kind of model going to run, to sort of get it to converge, I guess you could say. There's other, things about convergence there as well. So that's just sort of a computational aspect of the model of how this is going to, arrive at its results. Then we sort of have, our formula here, you can think of this as. We specify main effects of treatment, time, age, education, and, all those other interactions we mentioned before. This is, another thing, statistical fact that we're not going to talk about right now. This is our estimation method, which is just, again, more of a computational thing about how the model runs. But it does have, practical statistical effects. We want descriptives, and we want, the results of the model, and we want all those estimated marginal means we specified. So we're going to highlight this all, and we're going to run. And now we get this. We get all our descriptive statistics, which, you can review if you want, but we'll just sort of quickly kind of brush through the rest of this here. We get, the number of levels that are each variable, so that's just a good way to check to make sure things look as you expect them to. Here's the type 3 test of fixed effects. So these are going to be, the main tests of significance. So we do see that there's a significant effect of time. So that means scores did change over time on average. They did depend on age. They did depend on education. They did depend on, the effect of treatment did depend on age. The effect of treatment did depend on time by age. So, the crucial treatment by time effect, which we see actually is not significant here, 0.493. We see it also was actually close to, but actually not, dependent on age as well. And so here we have the estimates of fixed effects. And so if we kind of go down to, our crucial test here, which is, treatment by time, we'll see that, in this line here, this test is not significant. So every categorical variable will have reference levels. So you can only compare, the control group to the treatment group. But after you've done that comparison, we don't need to and can't really compare the treatment group to the control group. It's the same thing again. So there's going to be these two reference levels. The treatment group serves as a reference level. The pre-score, as compared to the post-score, serves as a reference level. And then when we measure their interaction, there's kind of only one more comparison we need to make. This has to do with degrees of freedom, which we won't get into today. But we see, this is not a significant effect, so that there's no interaction, again, supporting what we saw earlier. If we go down to estimated marginal means, we see the overall effect, the effect by treatment, but we're just going to kind of go down to that time by treatment effect, given that that's what's of most interest to us. And so what we're seeing here is we're seeing that, the memory score in the post group for those in the control group is around 66, but their pre-score was around 76. So it seems like they dropped 10 points, through the intervention. Whereas for the treatment group, they went from 75 to 76. So they actually increased a point. So this is sort of a bit surprising because it seems like there's like an 11-point difference in the treatment effect, whereas, people in the treatment group dropped 10 points, people in the control group dropped 10 points, people in the treatment gained 1 point. So 11 points on a 0 to 100 scale seems like a pretty large effect, to some degree. So we might wonder why this happened. So one reason could be that all these interaction terms we added in, sort of soaked up some of the variation. And so we can go back to our model, and we can say analyze, mixed models, linear. It's going to take us right back to the same menu. And so if we go to our fixed effects here, what if we just, take out a lot of these sort of extra interactions here, and we just remove all those. So now we just sort of get it to this, kind of simple treatment, time, age, education, and, treatment by time. We'll even take out age and education for now, just to really strip the model down. We can continue. Might want to, I'll just leave this as is. So we'll go ahead and paste this. So now we have this stripped down model that will run, and let's see what happens here. So again, let's just kind of scroll down to that, tests of fixed effects. So now we do see this significant treatment by time interaction. And so if we go back to our treatment by time estimated marginal means, again, we're seeing something very similar. They drop 10 points in the treatment group. In the control group, they gain 1 point in the treatment group. So it does seem that all those interaction terms we added were soaking up a lot of the variation attributable to treatment by time. And now this puts you in a position as a researcher to try to understand, were all those interaction terms that we specified, necessary? Why might that be absorbing the treatment effect? Is it actually that, the treatment, by time interaction is affected by those other variables, or were they just perhaps related by chance and it was just random variation that was, being soaked up by those extra interaction terms that was taking away from our effective interest? And so there's no way to really say that right now. That sort of more so depends on your theory than statistics, and so your knowledge of the content area of whatever it is that you're studying. So that will always be a question, for the researcher to handle themselves. But with that, I hope this was helpful. This was how to manage and analyze repeated measures data in SPSS. We looked at it just using a general linear model to begin with, accounting for the repeated measures, and then we transformed the data from wide to long and analyzed that using a linear mixed effects model, or what's just called a mixed model in SPSS. Both of these ways can be, handy ways to handle this type of data. I think, these linear mixed effects models are generally more useful, especially as your data and, repeated measure structure becomes more complex. And so it's a useful tool to understand. And there's plenty of, material. You can take courses and courses on linear mixed effects modeling. So there's much we didn't discuss today and sort of glossed over. And I hope you get the chance to look at that more in the future. Thanks.